Now we'll have a final review of the approaches that we learned this semester in biostatistics. Everything in research begins with a question, and that question will lead to hypothesis testing. So you start with an idea where you wonder, is this variable related to that variable? More specifically, is age related to blood pressure? Is blood pressure different for men compared to women? Is this new medication more effective than the standard medication in lowering blood pressure? The general approach is this variable related to that variable? Does this variable predict that variable? Is this variable different by the categories of another variable? That is your research question. That is what you aim to find out by using data. Your research question leads to the definition of your hypotheses. There are two hypotheses, the null hypothesis and the alternative hypothesis. Remember, the status quo, or the current situation, or what we currently assume to be true, is our null hypothesis. Our research question, or what we want to show, is our alternative hypothesis. Our null hypothesis assumes that there is no difference, there is no relationship, X does not predict Y, X is not related to Y, or Y is not different by X. What we are hoping to show using statistical evidence is that there is a difference. There is a relationship that X does predict Y, or that Y is different by the groups of X. So how do we do that? We need data. Data will give us evidence. We want to sample from a population. That's how we'll obtain our observations, whether they are people or units of observation or water samples, pollution samples, or hospitals. What we would like is a random sample. Random samples are the best way to get data that is generalizable back to a population. That is, it represents the population well. Oftentimes, convenient samples are more practical. If you are operating with a convenient sample, try to sample as many different types of people or from as many different locations as you can. There are two types of studies. Experimental or interventional is one, with the randomized controlled trial being the gold standard. That is where you take a unit of observation, usually a person, you measure them, then you perform some kind of experiment or an intervention, and you measure them again for change. These types of studies are very expensive and can take a long time to complete. What is frequently done are observational studies. So you are doing a survey or you are observing a cohort of people over time. In this case, doing an observational study, you want to try for a random sample. What types of data do we have? Well, if we think about data in terms of whether or not we can estimate a mean from it, that is, can we take all of the numbers, add them up, and divide by the number that we have and get a mean or an average, then that is a continuous or numeric value. Is your data captured in categories? If it's captured in categories, how many groups are there? If we look at sample demographics, gender, that is a categorical variable. That will be reported in the N of each gender that you have and the percent that you have. Age. Age is a variable that could be collected numerically or as a category. How old they are right now, captured in years. Then you could report a mean and standard deviation, a median and IQR, which is the interquartile range, or a median with the minimum and maximum. Age could also be captured categorically in groups where people check a box. They tell you they're 20 to 25 years of age or 26 to 30 years of age. You cannot calculate a mean if age is captured in groups. Race is categorical. You would report the N and percent in each racial or ethnic group. Weight. Weight is another variable that could be captured as a number. How many pounds or kilograms does someone weigh in a number? Weight could also be captured as a category where someone checks a box that indicates that they weigh between 150 and 159 pounds. If it's captured in categories, you cannot create a mean value from that. You will report N in percent within each category. If you capture weight as a continuous number, you could then combine it with height to create the body mass index. Body mass index is another variable that has a continuous measure, the actual number, but can also be divided into categories such as normal weight and overweight. Income level, similar to age and weight. You could ask somebody for their precise amount of income, but often people check a box for income. When they check a box that indicates that they make less than $50,000 a year, $51,000 to $60,000, you cannot capture or create a mean from that. That would be an N% reporting. If you can collect data as a number, collect it that way. Ask for someone's age. Let them tell you what their age in years is. You can always create a category later. If you capture someone's weight by using checkboxes, you cannot take that weight and create BMI. If you do not know their exact weight, you can't use it in a formula such as a mean or such as BMI. If you can collect data as a number, collect it as a number. You can always create categories later. A little bit more about categorical data. There are 3 general types of categorical data. All of them are reported with N in percent. The simplest type of categorical data is dichotomous data. There are 2 response groups. For example, yes or no, high or low, exposed or not exposed, disease or no disease. Order doesn't matter with 2 groups. There are only 2 groups. You cannot put one high or low or high. Analyzing them is the same either way. Nominal categorical variables mean that it's in name only. There's no order to the groups. An easy way to think about this is hair type: blonde, brown, red, or black. Retired, employed, or not eligible to be employed. Ordinal. Ordinal means there's an order to the groups: high, medium, low. Stages of cancer: 1, 2, 3, 4. There is an inherent order, and ordinal variables can be reported in cumulative percents. That is, I could look at high versus medium and low. So I could combine the medium and low percentages together. I could look at stage 1 and 2 versus stages 3 and 4, or stages 1, 2, and 3 versus stage 4. It makes sense to look at those variables in that manner. It does not make sense with nominal variables to report them in cumulative percentages. Once we have our data and our question specified, we need to use our analysis to bring evidence that we need to answer our question. There are 3 types of analyses: contingency, group means, and correlation. All of them will use fit y by x. The 3 bivariate analyses that were considered, utilizing a fit y by x, where you have one predictor or x variable and one y variable, were contingency table, group means, and correlation. For contingency tables, the question is the percent of y different by x groups? In this case, both variables are categorical, and a chi-square test is used to compare the percentages. You can see that you get a table with the rows of your predictor and the outcome as your columns. And the likelihood ratio chi-square test will answer the question if the proportion of those with a yes response is different by gender in this example. In group means, the question is the mean of y different by your x groups? Your y is a continuous measure here, and your x is categorical. When you have 2 groups in x, a t-test compares the means. When x has 3 or more groups, this becomes ANOVA, and you use an f-test. And finally, in correlation, the question is, are x and y related? Both variables here are continuous, and you can assess the correlation, or R, as positive or negative a positive correlation meaning that as X increases, Y increases, and a negative correlation meaning that as X increases, Y decreases. You can test the correlation equal to 0, or you can test the line of fit slope equal to 0. In both cases, a significant p-value will tell you that the variables X and Y are related. How do we make our decision? We use the p-value to choose between our null and alternative hypotheses. For H0, we will choose H0 if the p-value is large or greater than alpha, and our alpha is usually 0.05. To choose HA, we'll choose that if our p-value is small or less than alpha. Which p-value do you use? If your null hypothesis is that A is not equal to B, that is a two-sided p-value, indicated by the absolute value. If you're looking to see if A is bigger than B, that's a one-sided p-value for superiority. And if you're looking to see if A is smaller than B, that's a one-sided p-value for something being inferior. You can see how those align from the JUMP statistical software here with the example from the prior panel. For a chi-square test, the automatic result is a two-sided p-value. If you would like the one-sided superiority p-value, divide that p-value in half. An extension to the bivariate analyses is modeling. An extension to ANOVA, where you have a grouped or categorical X and a continuous Y, is ANCOVA, analysis of covariance, where in addition to your main categorical predictor, you also add other covariates, perhaps age or gender, or a baseline starting value. An extension to correlation is linear regression or multiple linear regression, where in addition to your main continuous predictor, you also add covariates of interest. And an extension to a contingency analysis is logistic regression. So in addition to your categorical predictor of interest predicting a categorical outcome, you can also add covariates. All of these follow the same steps. The first step is to conduct a whole model test to determine if a model is needed. Your null hypothesis is that either the mean of the response or the proportion experiencing your event or outcome of interest is the best estimate. And your alternative hypothesis is that a model is useful. If the model is not needed, then simply report your univariate descriptive statistics and your bivariate results. If the model is useful, you will then use the appropriate statistical tests to determine which variables contribute to your model and how they contribute to predicting the outcome. These are the steps that we use with sampled data from a population that allow biostatistics to provide evidence for public health for associations between variables, changes over time, will help us determine impacted groups and populations, and target resources to improve the public health in those impacted groups and populations.